Hello, this is Roberto and this is the HVAC is my channel. Today we're going to be talking about grills, registers and diffusers selection part 3, okay? So the difference is now we're going to be explaining about ASHRAE 70, which is the testing method for performance for air outlets and air inlets, okay? Okay, so let's start little by little. Since this is the HVAC is my channel, what I'm gonna do in here is I'm gonna put the following. So this is the temperature. So we have two temperatures. One temperature, see, the temperature is gonna be the room temperature, and the other one is so one is the air temperature and the other one is the supply temperature. So temperature of the supply, see, supply, okay, supply, okay, and then we're gonna have another temperature, temperature of the room temperature, see, room temperature. Okay, so that's the difference. So what I'm gonna do is also I'm gonna draw, see, a room. Let's go here, a room. There we go. That's a room, and then I'm gonna have my diffuser here. There we go. Okay, and then I'm gonna make a line in here. So like this, like this, something like this, or something like this. There you go. All right. Okay, so pretty much this is what happens. So this is my room. I'm gonna put in here, this is my room. Okay, so this is kind of my airflow pattern. There we go. So it's going like that way. And this is my ceiling diffuser. So originally I'm gonna make this another color. So let's make let's make red, or let's make pink. Okay, so in here I have two temperatures. This is temperature of the supply air, right? And the other one is temperature of the room. Okay, let's make this a little bit better in here. So in here is temperature of the room, TR. Okay, so for example, now everyone knows that in reality, I'm gonna put in here reality. So when we're talking about in reality, what's happening for real is that I'm gonna put this in yellow. So what is real is the temperature of the room is not equal to temperature of the supply air. That's in real life, right? So this is what is called non-isothermal conditions. Okay, so I'm gonna put in here non-isothermal conditions. I'm gonna put in here non-isothermal, isothermal. Okay, non-isothermal. So what is iso? Iso means equal, thermal means temperature. So this is saying like it's not the same temperature. So iso equal thermal temperature. So it's not the same temperature. So in real life, this is not going to be the same non-isothermal conditions. And ASHRAE, actually, ASHRAE Standard 70, see, ASHRAE Standard 70, I'm going to put this in pink so it looks better. So ASHRAE Standard 70 has testing procedures. So ASHRAE 70 has two testing procedures for both. So it has for non-isothermal and for isothermal. However, so ASHRAE, so for air devices, so ASHRAE, I'm gonna put in here in pink still, ASHRAE, however, ASHRAE 70, okay, makes the assumption in order to simplify the concept and everything, to make it more consistent for comparable results. So they make the assumption of temperature of the room temperature is equal to the temperature of the supply air, right? Of course, it's not going to be the same, because what happens, you know, we have winter, we have summer. Of course, this is not going to be the same. If it would be the same, that there's no need for AC. It's the same. So in winter, this is going to be cold. In summer, this is going to be hot, right? So it's not the same. So this is the real situation, and that's called non-isothermal. But ASHRAE 70 makes the assumption that TR, which is room temperature, equal to the temperature of the supply. So this is what we call isothermal conditions. isothermal conditions. All right, so the standard actually make these tests, and I'm gonna put the section of the test, and you can check it online. So the test is called, I'm gonna put in here the section. So this is section, I'm gonna put section in here, section of standard ASHRAE 70. Check it out. So for isothermal, non-isothermal, for non-isothermal it's gonna be 5.4.4, and then for isothermal it's gonna be section. Let's put section isothermal air 5.4.3. Okay, now we know the difference. And then what happens is, why this is so important, because actually our performance data so this is the performance data, of usually air devices are based on isothermal conditions. If you want to go deeper on this, you can always check ASHRAE 70. Okay, so now what we're going to do is I'm going to show you that small piece of information in here. Let's go to my next to the next screen. Okay, for example, this is ASHRAE Standard 70. So in here we can check, this is completely ASHRAE Standard 70. See, ASHRAE Standard 70 2006. Of course there's more updated versions possibly, I'm not very sure actually, but let's go here, and it says in here, see, section 5.4.3 test procedure using isothermal air. So we have actually two sections in here. See, this is the I'm gonna put this in here like this, test procedure, there you go, test procedure using isothermal air, and the other one is going to be test procedure using non-isothermal air, right? So pretty much in here is explaining to the manufacturers how to run this test based on this standard. And then you're taking, see, basically based on the 170 FPM terminal velocity. And you can always go deeper on this. But I just wanted to show you that part of the section for isothermal. And then what's the reason for this analysis actually? Again, like we saw in the previous video, most of the catalogs and performance for air devices for each manufacturer, they bring up this topic about isothermal conditions. And honestly, when I was speaking to representatives, they always make sure that the language is correct. So this is based on isothermal conditions. For example, again, I'm going to bring this up, and I opened up air performance PDFs of other manufacturers. For example, in here we're going to check, let's go check in here. In here we have the following. So for example, we have for price. So for price industries, we have a catalog. So in the catalog for performance data, of course, this is always available online. And for example, architectural perforated diffuser, we're going to go check down here. Let's go check down here a little bit more. So there we go. We have performance data, and then under the performance data, let's go to the notes. In the notes, there we go. So we have the notes in here. So on the notes, what does it say? Okay, so performance notes, it says tested in accordance with ASHRAE Standard 70 2023. Okay, so I was saying I'm not very sure about this. I'm not very sure, but actually they updated this. So standard ASHRAE 70 2023. I'm sure it's available online for purchase, right? Okay, so this is the method of testing for rating the performance of air outlets and devices, right? There we go, air outlets and devices. So see, what happens in here is that price is indicating that on the notes. And of course, when you're doing your schedules for your project, you can always put under the notes, this is tested based on ASHRAE Standard 70 2023 or 2020. 2023 actually, and you can always double check with the representative. Okay, so we're gonna go to Titus as we were seeing in the other video. So in the other video, performance data, again seeing here what it says: data obtained from tests conducted in accordance with ANSI ASHRAE Standard 70. Actually, this is based on 2006. That's very interesting. So that's another piece of knowledge for everyone. So price is based on 2023, and then for Titus is 2006 actually. Sometimes I make mistakes by mentioning stuff, so if I make a mistake, please forgive me about that. So for example, I would say instead of 2006, I would say 2023. No, not really. Okay, I'm gonna be more careful on that. So ASHRAE Standard 70 2006. All right, so see actual performance with flexible duct inlet may vary in the field. See engineering guidelines for this catalog for additional information. So what is interesting in here, it says if the diffuser is mounted on an exposed duct, the throw values are 70% of those listed in the table. For example, in here what we have is the throw. See, on the other video we were checking that, for example, the throwing feet, these 5 would be at terminal velocity of 150, 7 would be 100, and then 15 would be terminal velocity of 50 fpm. So what this is saying is like, for example, if your diffuser is an exposed duct, you don't have sealing, right? So if you don't have sealing, so they are saying that you have to take actually 30% of this 15. So for example, in here, 30% of 15, you need to take into account 70% actually. 70% of the 15.7 equals. So actually the real throw is 10.5 because it's 70% if it's exposed sealing. So this is something to consider, and this is very important actually for more accuracy, right? So it's important always to look at the notes. I understand sometimes the engineers are very busy, but this is showing better value on your design. Okay, throw values are given for terminal velocities 100 and 150, 150. And forgive me for the redundancy, but this is always very important for us to keep in our minds. Okay. Okay, we're going to go check in Green Hex. So that's another manufacturer for air devices. So in here we have a model ceiling diffuser square cone. See, 24 by 24, CFM, static pressure, total pressure throw. See, we have the throws in here. Again, terminal velocities, 150, 150. Okay, so we're going to go in here to the notes. Okay, let's check. Oh, again, it says all data is tested in accordance with ASHRAE 70 2006. There you go. Okay, so again in here it says, oh, this is very interesting actually. It says the throw in star, it says non-isothermal. See, non-isothermal is the reality. That's what happens in real life, right? Horizontal throw. See, the supply air temperature is 15 degrees colder than the average room temperature. Okay. Okay, so the supply air temperature, of course, that's what happens, all right? Values are for 150, okay, velocities. So this is very interesting because there is a rule of thumb. There's a rule of thumb that says the following. So you need to reduce the percentage by 1% based on the delta T. This is the delta T actually. 15 is delta T, 15 degrees. So technically in here it should decrease, that throw should decrease in 15%. So if the temperature difference is 15, it should be 15% of decrease, okay, of the throw. There you go. Okay, so we're going to check that in here. See, look at this. For example, let's check on this. Let's make an example. I just want to be in here a little bit more playful. We're going to make like, okay, let's check on this. 18 times 0.15%. So that would make it 85. So that's going to be about 15. So maybe this is not correlating because every manufacturer is different. Okay. So let's go. I'm going to explain this a little bit later, but we're talking about the isothermal conditions. So it says isothermal throw, isothermal conditions. Supply air temperature is the same as the average room temperature. That's what we're talking about, right? Based on ASHRAE 70. And the values are for these velocities. Okay, so in this case, this manufacturer is making this, they're making the design. So as I said before, this is a rule of thumb that I was mentioning. So it's not applicable for everyone. So it's important to read on the notes. For example, in the green heck, it's not very much applicable. But now I'm gonna make, so now we understand what is isothermal and non-isothermal, right? Okay. So now what we're gonna do is the following. Okay, so in this room in here, I'm gonna put this in, let's see, in orange. So we have 3 points, right? 1, 2, 3. There you go. So those 3 points. I'm gonna make my line in here on the other side, so that way we understand better. So let's see those 3 points like this. Those 3 points, and this is coming from, actually no, I'm gonna make it like actually I'm gonna change colors. I'm gonna make it like yellow, and let's see again, I'm gonna have my diffuser here. I have my diffuser, ceiling diffuser, and then I'm throwing air in here. Let's go throw air like this. There you go. And then I'm gonna make it in here orange. Okay, so we're talking about 3 terminal velocities. Oh, what's going on? Okay, what's going on? Oh, I see what. Okay, hold on, just hang in there. I'm just trying to make this a little bit neat. Okay, here we go. Terminal velocity, so that's going to be T150, and then this is going to be, it's not terminator, right? So T100. So let's check in here. T50, terminal velocity of 50. There we go. Okay, so what happens is I'm gonna put this in pink. So okay, let's make in here as pink. We need to understand this T supply air and T room temperature, right? Temperature of the supply. Okay. So we need to talk about the delta, and the delta is it is T of supply air minus T of room temperature. Okay, that's the delta. This delta is very, very important. Okay, that's the delta T. So in this case, we're gonna see the effect. So delta T. Okay, so when the throw is 150, this isothermal part and non-isothermal part has minimal effect. Minimal effect on the throw. Minimal effect. We're talking about the throw, right? So minimal effect on throw. Minimal effect on throw. Okay, so it doesn't matter if you are talking about the terminal velocity of 150. You don't have to worry about in the catalog. Okay, the catalog, for example, is going to be like, let's make an example in here very quickly. So, for example, I'm gonna go check to my catalogs. We're talking about, for example, Titus, and we were talking about this model. These guys right here. Okay, so in here it says 124. This 124 is okay, I would say, but let's go with bigger CFMs that are very critical. So for example, this. So 473. Let's go for 473. For example, if my throw is 473, there you go. I'm gonna put in here throw. So let's make this in yellow. So for example, my throw is 4, 7, and 13, and this throw is in feet. Okay, there you go. Okay, and this is based on again, this is based on isothermal conditions. Isothermal conditions. That's what the manufacturer says, right? Isothermal conditions. Okay, So see, if the throw is like 473 isothermal conditions, see these, I'm gonna make again this in pink. These 4, which is 4 feet, is gonna have minimal effect on throw, which means I understand that the delta T is not the same. So the delta T in here we're applying, I could say delta T. Let's put in here. So technically in here my delta T would be 0, right? Because they are the same. I'm sorry, this is not isothermal. Oh, let's put 0 in here, but different than 0. Whereas in here my delta T equals 0. See, there's no exchange on temperature. So based on isothermal conditions, delta T 0, for T150 thermal velocity, it's okay. Don't worry about it. That's what it's saying about the ASHRAE 70. So isothermal conditions is not real. Okay, let's do this actually. You know what? I don't want to confuse anyone. Let's continue with this another column in feet, and this is the reality. Non-isothermal. This is the reality, right? Because what happens is when you're designing your building, you need to consider this to be more specific: isothermal, non-isothermal conditions. Okay, which is the real life. Okay, so 4 is 4. I don't care. We're fine, right? Okay, so what about 7? For 7, I'm gonna be like, it's a bit affected. Slightly affected. So I would say in here it's a, let's for example put in here, instead of 7, let's put maybe 6, slightly affected, right? Not so much. So the big issue is this one. This is the big issue, which is like T50, terminal velocity of 50. Then we have a 13 feet of throw. That's the one that is gonna be affected. I'm gonna put in here affected. This is affected. And again, a standard 70 assumes isothermal conditions. Yeah, you know, why are they doing that, right? You might be wondering, why are they doing isothermal conditions if it's not the reality? So the assumption, because the assumption makes it more consistent. So the assumption, I'm gonna put in here the assumption makes it more consistent for comparable results, more consistent and less difficult, less complex. See, less complex. Okay, so that's the reason ASHRAE 70 is doing that. Okay, now we were talking about the 70. 70 is the one that is going to be affected. So how are we going to address this? Okay, so what I'm going to do is in here, this is going to get affected a little bit. So let's go here. So we're going to be focusing on this T70. So what happens is we have a good rule of thumb, ROT. Okay, so this is a rule of thumb. Okay, so what is the rule of thumb? We're saying that depending the temperature, delta T equals to the percentage of degrees Fahrenheit. Okay, so for example, so if delta T equals 15 degrees Fahrenheit. Okay, so what was delta T? Delta T was the difference between the supply air and the room temperature. So of course it's gonna be different because we have winter or summer, and that's the main reason of air conditioning, right? To make it comfortable for the occupant. So there is always gonna be a delta T. For as an example, if the difference between them is 15 degrees, so it's saying that the throw, so this is for the throw. The throw equals a change in 15%. There we go. Okay. Now this 15% could be increase or decrease, right? So that's why I'm doing this little by little. I want this still to be the HVAC easy math. I don't want to make this the HVAC difficult math. So I don't want to lose my subscribers. I always want to, this is even for everyone that is interested in getting deeper and deeper in HVAC design, okay? All right, so let's understand this a little bit better. When does it go up and down, okay? So I'm gonna put this in a different color so that way it's better. Hopefully I'm not making a mess, hopefully. So this is gonna be very easy. So let's put this when it's ceiling, horizontal, or yeah, the most important one. So ceiling, so if it's ceiling diffuser, right? And you're gonna have a horizontal ceiling, and this is horizontal throw. All right, so horizontal throw. We're gonna have an increase. Let's do this a little bit better. This is for ceiling, that is horizontal, the most common. For ceiling, that is horizontal throw. We're gonna have that this increases, but again, I don't want to confuse everyone. Hopefully you're not confused yet. I'm sorry about that. Okay, again, let's do it little by little. This is a ceiling diffuser, this one, right? Okay, what is it doing? It's horizontal throw. I'm gonna make again this something because this is a ceiling diffuser. So where's the ceiling, right? So the ceiling is right there. See, when I make these lines, is they mean that they are the ceiling. There we go, ceiling. This is the ceiling diffuser. All right. So for this case, the ceiling diffuser horizontal, we have two modes of operation. So number one is heating, right? I need heating in winter, it's very cold, and I need cooling in summer, it's very, very hot, right? So heating and cooling. There we go. So for this configuration, ceiling horizontal, heating and cooling. In heating, I'm gonna have an increase, okay? So for heating, I'm gonna have an increase. So this is an increase. Increase. And this is gonna be a decrease. Decrease. Okay, so what am I saying that? What's this? An increase and increase? Yes. Here's what's happening. Okay, so for example, I'm talking about the throw, right? So the throw is 13. Okay, that's interesting. Why? Because are we talking about heating or cooling? So this is based on isothermal conditions. It doesn't matter, right? It's 30. I don't care. But when it matters, is like 13. Okay, so for example, I'm going to put an increase and decrease in heating and cooling. Say, for example, my delta T is 15, for example. So 15 means a change of 15%. Of course, this delta T is going to be maybe in summer, it's going to be maybe 20, right? So let's make, for example, in here, heating is going to be delta T. Hopefully you're not getting lost. I'm going to have to make another video. 15 degrees. And then in here, delta T is going to be 20 degrees. There you go. That's an example. Okay. So in heating and cooling and in summer, and okay, 15 degrees. So that means an increase of 15%. Increase of 15%. So there you go. And this means a decrease of 20%. Okay. So what am I meaning for this by this? So what is an increase of 15%? We're going to make the calculation in here for the throw. We're talking about the throw, right? So the throw right now is 13. So that's going to be an increase. 13 times 15%, 0.15. What is that? So that's going to be an increase of 15%. I'm going to bring my calculator. And then in my calculator is, what is it? 13 times 0.415%. So that's going to be 1.5. 1.5. Okay, for this is going to be a decrease. So 13 times 20%. Why is it 20%? Because it's 20 degrees delta T, for example, right? So I'm going to put 0.20, and then what is that? So what that's going to be in here again, 13 times 0.20%. That's going to be 2.6. Okay, wonderful. So what happens is, if this is heating, see, I'm gonna put in here. There you go. So for example, if this is heating, my original isothermal conditions was 13. 13 plus, I'm sorry, is not, yes, plus, because it's an increase. So 13 plus 1.5 is going to be 14.5. It increases. And for example, for cooling, it's going to decrease 20%. 20%, why? Because I'm assuming my delta T is 20. Okay, delta T, and so this is going to be 13 times 20, 2.6. It decreases 2.6. So again, HVAC is math channel, easy math, go easy or go home. 13 minus 2.6, 10.
Sorry, I don't understand.
Sorry, that was my Google device. Okay, so in here we're going to have 14.5 and then 10.4 in non-isothermal condition, and this depends on the configuration of the diffuser. For example, this is the last part, and I'm sorry for this mess. So we're going to have ceiling horizontal. This is also applicable for sidewall, and this is applicable for floor diffuser, for floor. But the only opposite one will be the ceiling vertical down. Okay, so I'm gonna put in here ceiling floor down in red. So ceiling diffuser vertical down is opposite. What do I mean by opposite? It means instead of increase, decrease, instead of decrease, increase. So that's the only, this is the rebel. Ceiling vertical. So for example, vertical down. So that's the only one that is going to be the opposite. The rest are going to be the same. Just and the reason is actually depending on buoyancy, because when you're heating something, it tends to when you're heating is more buoyant, okay, less density. When it's cooling, it's denser, so it's heavier, right? It's heavier, so it travels shorter. Okay, so yeah, I hope you enjoyed this video. But and also see, this is the terminal velocity that got affected, right? Terminal velocity. Again, let's put this as terminal velocity, because I don't want anyone to get confused. What is T, right? Terminal velocity. And then T, this doesn't matter. Minimal effect, we don't care about this, right? All right. So this is the room temperature. What else am I missing here? This is ceiling diffuser. I'm gonna put in here this is the diffuser. Ceiling diffuser. All right. Okay. I'm sorry for the length of this video, but I always have seen that the manufacturers, when you are coordinated with them, you see on the performance devices, it always shows as isothermal conditions, and that's why this video was important, and that's why I went a little bit farther. I'm sure I'm gonna make more videos about this, because selection of air distribution is very important. Okay, please hit the like button, it's very important for me, and share this video and leave any comments and subscribe. Okay, I'll see you in the next video. Thank you.